Okay, I'll go ahead and share the PowerPoint. And again, anybody who logged in a little later, make sure that you log in the Top Hat. We are going to use that for questions today. And then also get the PowerPoint off Canvas. The entire thing is up there. It's in the complete notes. Okay, so today we're going to talk about nuclear magnetic resonance, which is NMR. I forgot to delete and mass spectrometry from this title, so we're not talking about mass spec today, because we've already done that. The big idea in this chapter is that by the end of the chapter, we're going to combine all of the spectroscopic methods that we've learned so far. We're going to talk about IR and mass spec really briefly again. And then we're going to use NMR as well to actually determine the structure of an unknown compound. So what you might remember when we talked about IR is that spectroscopy is the study of the interaction of energy with matter. Nuclear magnetic resonance, which we'll call NMR from here on out, is basically energy absorbed by molecules in a strong magnetic field. There are characteristic energy absorptions that indicate structures of a molecule. There are some patterns that you can learn to recognize. We're going to go into a little more detail about NMR in a second. Previously, what we saw was IR spectroscopy. We use this largely to determine the presence of functional groups. And then we had mass spec, which had molecules bombarded with the beam of high energy electrons, and we were able to determine the molecular weight of a compound and also analyze fragments, which we didn't focus on too much. We mostly looked at the molecular weight, but fragments can also help. So NMR spectroscopy is, it can be very, very specific in a really cool way. No two molecules will have the same NMR, and the NMR can tell you exactly how a molecule is put together. So NMR characterizes organic molecules by identifying carbon-hydrogen frameworks within molecules. So if you can use the NMR to determine the carbon-hydrogen framework, and then you know the functional group present, maybe from the IR and then supported by the NMR, you can actually come up with the exact structure of the molecule. The most common types of NMR spectroscopy are proton NMR. Can everybody make sure that you are muted? So the most common types of NMR spectroscopy, the first one is proton NMR. This is the one we're going to talk about the most. It is the easiest to interpret, and it also gives you the most information. So this is used to determine the type and number of hydrogen atoms in a molecule. Carbon-13 NMR is used to determine the type of carbon atoms in a molecule. And we'll talk about why carbon-13 is not as easy to use as proton NMR in a bit. The source of energy in NMR is radio waves, which have long wavelengths and thus low energy and frequency. When low energy radio waves interact within a molecule, they can change the nuclear spins of some elements, including protons and carbon-13 atoms. Only nuclei that contain odd mass numbers, such as hydrogen 1, carbon-13, fluorine-19, and phosphorus-31, or odd atomic numbers, such as deuterium and nitrogen-14, can give rise to NMR signals. So the basic theory behind NMR, this is not something that I'm really going to make you stress out about. I just want to explain it a little bit so that you can kind of understand where this information comes from. The theory behind NMR is essentially, starting over here on the left, when there is no applied magnetic field on a molecule, the nuclear spins of all the different atoms are random. So you have a bunch of different atoms in a molecule. The nuclei have spins, and they are all randomized. Remember also that the spin creates a dipole, creates essentially a magnetic field around the atom, which makes these nuclei kind of like tiny bar magnets, is how they describe it, which creates a magnetic moment. So when the molecule is just existing on its own, it's randomized. There is no overall magnetic moment of the molecule. But if you apply an external magnetic field, these atoms can align. And then there will be an alignment with the field and an alignment potentially against the field. And usually there are more molecules aligned with the field than against, and so you have an excess of those aligned with the field. This is a lot more detail than I'm ever going to ask you about, again, just in case you're panicking. So these atoms can either be spin down or spin up, essentially. And, whoops, that's not the slide I thought was next. That's okay. So you can think of this kind of like if you've ever played with like a Woolly Willy toy. There is, the dude's face, and then there's a bunch of like iron shavings, and you can shake it around and they just move wherever. But you take the magnetic thing and you put it on top, and all the magnetic pieces line up to the magnet, right? And then you can drag the iron hair around and decorate Woolly Willy however you want. That's what's happening here. Like all those nuclei, they have their own magnetic moment, but they can line up if you apply an external magnetic force. So the way that we read proton NMR is there's a certain number of signals in the spectrum, and this will tell us how many different or unique proton environments there are in that molecule. The position of the signals in the spectrum tells us about the magnetic environment of each set of protons. So the position of the signals is called the chemical shift, and the magnetic environment is affected by the presence of electron withdrawing groups. And we'll talk about their direct effect in a second. The area underneath the actual signal that's coming from the NMR is called the integral. So this is taken straight from math, right? And the integral is the area under a curve. This tells us about how many protons there are in the set being measured. And then the last thing that you can get from proton NMR is by looking at the multiplicity, which is called the splitting pattern of each signal, which tells us the number of protons on atoms adjacent to the one whose signal is being measured. So this is a lot of words. We're going to go through each one of these things individually. So first up, the number of NMR signals equals the number of different types of protons in a compound. Protons that are in different environments give different NMR signals, and equivalent protons will give the same NMR signal. So for example, in these molecules that we're looking at, the first one is dimethyl ether. There's a plane of symmetry through the molecule. So you have two different carbons, or sorry, you have two carbon atoms, but they are the same because there's a plane of symmetry through the molecule. And then you have 6 hydrogens, which would be considered identical because these carbons are both methyl carbons attached to an oxygen. There's nothing that makes either of these carbons different from each other. If we took the molecule and flipped it over, it would be no different to us. So that means that these hydrogens are also completely equivalent. So if you were to take an NMR of dimethyl ether, you would see one NMR signal because there's only one type of proton on that molecule. Now in our next molecule, we have chloroethane. There are 2 different hydrogens present in this molecule, so we would see 2 NMR signals. Now the reason they're different is because these hydrogens are on a secondary carbon, it's attached to a chlorine. It's what a CH2 group is called a methylene carbon. So these are methylene hydrogens. They are directly adjacent to the chlorine, but the carbon that's a methyl group over here is separated from the chlorine by another carbon. So these hydrogens are experiencing very different magnetic environments. Additionally, this is a CH3 group, so there are 3 hydrogens on this carbon versus the CH2 group where there are 2 hydrogens on that carbon. So any degree of difference is going to cause them to have different magnetic environments. Now the next molecule over, we have ethyl methyl ether. This has 3 different types of carbons, 3 different types of hydrogens. This is going to give 3 NMR signals. So this methyl group is different from the other methyl group, so HA and HC, because HA methyl group is directly attached to oxygen, but HC is separated from the oxygen by CH2. So there is no plane of symmetry through this molecule. So all 3 of these different sets of hydrogens are unique. Does this idea make sense so far?
Yeah.
I'm clicking through
Yeah, it makes sense.
all of you guys real fast.
And I think we'll have to see the visual differences.
Yes, we're going to look at a ton of spectra today. So to determine equivalent protons in cycloalkanes and alkenes, you always need to draw all the bonds to hydrogen. So when you're analyzing a compound like chlorocyclopropane, do not draw out the structure on the right-hand side. Instead, draw out the 3D image, because in the 3D image, you can actually see that there are a lot of different protons here. So if we had just looked at this like this, we would probably think, okay, this is one type of hydrogen, and then these 4 are equivalent. That's the way that it looks when you draw the molecule flat. But when you draw it in 3D, what we actually have is this hydrogen is unique. These 2 are a unique set, and these 2 are a unique set, because these hydrogens are having axial interactions with the chlorine, whereas the hydrogens underneath the ring are not. So even though these are both CH2 hydrogens on the same carbon, they are experiencing totally different magnetic fields at the moment. So you end up with 1, 2, 3 unique sets instead of 2 unique sets. So you need to draw it out in 3D. Same with alkenes. Drawing it out flat like this makes it look like you have this hydrogen and these, just 2 different ones. But what you actually have is this hydrogen, which is on the same carbon as the chlorine. And then you have this hydrogen that is on the same side as the other hydrogen. And then this hydrogen that is cis with the chlorine. So all 3 of these hydrogens are experiencing totally different magnetic environments. So drawing a structure out as fully as possible is always going to be helpful with NMR, specifically when it's cyclic or alkene. Excuse me. So when you're comparing 2 hydrogen atoms on a ring or a double bond, the 2 protons are equivalent only if they're cis or trans to the same groups. So in the molecule here on the left, these hydrogens are identical because they're both cis to a chlorine. The other way to look at this is there is a plane of symmetry running right through this molecule. That makes these 2 hydrogens identical to each other. In the next molecule over, HA and HB are different from each other because HA is cis to a chlorine, but HB is cis to a bromine. There is no plane of symmetry running through this molecule, so you're going to end up with 2 unique signals. And then in our last example, I believe this is the example from the previous page, but HB is cis to chlorine, whereas HA and HC are both cis to hydrogens. But you also have to take into account that HA is on the same carbon as the chlorine. So you end up with 3 unique signals again. And then this is essentially what I drew out on the previous slide. You end up with 3 different signals because these are cis to the chlorine. They're on the same face of the molecule as the chlorine. And all these hydrogens are on the same face of the molecule. And then there is a plane of symmetry that runs right through the molecule. But if you have a structure like cyclopropane, all 6 of these hydrogens are identical, and so you end up with one NMR signal. Okay, so here's our first NMR spectrum. So this is of bromoethane, and there's a lot of information here. We're going to keep coming back to similar spectra as we learn more information, but for now we're going to look at the number of signals. So in this molecule, we have a CH2 group and we have a CH3 group. These are 2 different types of hydrogens, and so we end up with 2 different signals. This third signal here is a standard that helps identify the location of 0. So it's just added to the sample so that when you take the measurement, this can be shifted in either direction. And then you tell the machine this is 0 and it relocates it essentially. Just for the sake of standardization across chemistry. Anyway, so that's why we have these 2 different signals, is because we have these 2 different hydrogens. The other information on here is the next topic, but I'm going to go ahead and kind of point it out to you now because this spectrum is so very clear. So what you might notice is that the protons marked B are split. This is not just like a single peak like this. It is split into 3 different peaks. Now, that's not because this is a CH3 group. It actually has nothing to do with the fact that this is a CH3 group. What it actually tells us is that our neighbor has 2 hydrogens. So a hydrogen set, a signal, will be split into N plus 1 peaks, where N is the number of hydrogens on the neighboring carbon. So since the neighboring carbon has 2 hydrogens, this peak is split into 2 plus 1 peaks, which is 3. And that explains why the CH2 group is split into 4. Because if this were related to the number of hydrogens on that carbon, this wouldn't make sense. But there are 4 peaks here, and that comes from N plus 1. The neighboring carbon has 3 hydrogens. 3 plus 1 is 4. So you end up with 4 peaks. And these are referenced with kind of cutesy names of triplet and quartet. Does anybody want to guess what it's called when you have 2 peaks?
A doublet?
It is, yeah. Did you read ahead?
No, I've taken OCHEM once before, but I kind of remember this one before.
Sorry if you feel like I called you out a little bit. I didn't mean to.
No, you're good. You said the triplet and quartet, and I kind of clicked. I kind of remembered, but I was also kind of guessing. So
Yeah, I once mortified an IA of mine. He was teaching 1142 for me, and I went and subbed a Organic 2 class over the summer, and I saw him in there, and I knew he had taken OCHEM like 2 years ago, and I was like, what are you doing in here? And so he ended up telling the entire class that he was retaking it to bring his grade up. And apparently they all thought it was hilarious, and their group me was talking about how I really did that to him.
yeah, you called him out. That's funny.
Yeah, I feel bad about that still, but apparently he thought it was funny. Anyway, so are there any questions about the information I've shown you so far? One of our next topics is going to be about why is this one all the way over at 3.5 ppm while this one is at 1.5. We'll talk about what gives them their different positions in a bit. Okay, so the different positions is called chemical shift. So chemical shift is the term used for those numbers that we saw. So the chemical shift is related to this down here. So if we were looking at this peak, we would say it has a chemical shift of about 1.65 ppm, while this other one has a chemical shift of about 3.4 ppm. So it's just the number. And these chemical shifts are related to the structure of the molecule and also proximity to electron withdrawing groups. But first we're going to talk about the structure portion. So if you have a primary alkyl carbon and hydrogens on that primary alkyl group, so a methyl group essentially, it should appear between 0.8 and 1.2 ppm. If it's secondary, it should appear between 1.2 and 1.5, tertiary 1.4 and 1.8. I'm not going to keep reading this out loud because that would be really, really obnoxious. But what I want you to notice is that these shifts are predictable and you can start to learn them and learn to recognize them. As hydrogens get closer to electron withdrawing atoms, their chemical shift value will be larger. So notice that a hydrogen that is attached to a carbon that's part of an ether, even though this is a CH2 group or potentially a CH3 group, it's not down here under 1.5. It's 3.3 to 3.9 because it's next to an electron withdrawing atom. We'll talk about why that affects it in a little bit. Our alkyl bromides are going to cause it to shift as well, which is why the CH2 group in the previous structure was further down the spectrum. So the reason this occurs is that electrons shield the nucleus from the influence of magnetic energy. So think about the electron cloud around the molecule. If that electron cloud is very, very large, remember that the nucleus is the part that's magnetic. The nucleus is the part that's going to feel the magnetic energy. So if you have a large electron cloud, it's going to interfere with that. The chemical shift is affected by the amount of shielding or de-shielding a nucleus is experiencing. So the more dense the electron cloud is, the more shielded we say the nucleus is. De-shielding occurs when you have an electronegative atom that pulls the electron density towards it. So electron withdrawing atoms will draw electron density towards them, which de-shields the nucleus and moves the shift further from zero. So in our previous structure, the protons for CH2 were around 3.4 because instead of having a happy, shared electron cloud, evenly shared, what we actually have is bromine hogging the electron cloud, a small one around CH2, and then CH3 gets to have a little more of its electron density because it's kind of farther away from the bromine. But we have a dipole towards the bromine. And since we've taken away some of the electrons shielding these hydrogens specifically, they end up with a higher chemical shift. And it's because the bromine is literally stealing the electrons that are shielding the nucleus. Upfield and downfield are used to describe relative locations of peaks. So downfield references higher numbers and upfield references lower numbers. So this is the exact same information, just laid out visually, which I always think is so much more helpful. So regular alkyl hydrogens should be in this area. And then hydrogens that are coming off of an aromatic ring or attached to a nitrogen, sulfur, double bonded to oxygen, double bonded to carbon, they're going to appear in here. This is nice and wide and vague for you. Really excellent. The being next to an oxygen or a halogen is going to put you in this area here. This AR-H here is saying protons specifically directly attached to something aromatic, so it'd have to be directly on it. And then this is referencing specifically the aldehyde proton, not anything that would be on this carbon, specifically the aldehyde proton. And then this would be specifically this proton. So I think this is a much more helpful bit of information. And then just remember that it goes CH3, CH2, CH. And if you're wondering if this is something you should memorize, yes, definitely. So I want to give you a little bit more of a demonstration of chemical shift. So the chemical shift for the hydrogens on methane, which would have one signal, is 0.23 ppm. If you replace one of those hydrogens with a chlorine to give CH3Cl, that puts it up at 3.05. All we did was trade out one hydrogen for a chlorine. You trade out two hydrogens for chlorines and you end up with a ppm of 5.33. By the time you're at chloroform, CHCl3, you're at 7.24. That's the equivalent of a hydrogen attached to an aromatic ring. That is very, very different from the shift of methane, right? So that's one comparison for you. Our next one, we have ethane versus ethene. So the hydrogens on ethane, again, one signal, are at 0.86, but you trade out your single bond for a double bond, and now you're at 5.25. Our next example is visual. So benzene, the hydrogens on benzene would show up at 7.26. For acetaldehyde, you have two different types of hydrogens present. The one that's on the CH3 group is going to be at 2.2, but the aldehydic hydrogen is at 9.8. And then in our last example here, we have 1-chloropropane. Our hydrogen that's farthest away from chlorine is honestly hardly affected. It's at 1.06, which is pretty normal, maybe just a little high for a methyl group. The CH2 is kind of affected, not a lot, but by the time you get to this CH2 that's directly attached to the chlorine, you're at 3.47. So proximity to the electron withdrawing group has an effect on the chemical shift felt. So these are nearly normal. This one's not. This is not at all normal for a methyl group because this is quite electron withdrawing. But take a look at this hydrogen, just one alone. That is really, really a high chemical shift. This is just another chart explaining the exact same information again. So depending on how you like to look at your information, there is a chart for you. Okay, we're gonna go to Top Hat and answer one question. See, I'm learning how to organize my Top Hat a little bit better. So I indicated which question we're doing. Okay, we'll go ahead and take attendance because that gives you some extra points. Is nobody submitting?
We can't see.
I don't.
Oh, I'm so sorry. So the answer is yes, nobody is submitting, but because of me.
Yeah, you turn it off.
Sorry, my Wi-Fi is kind of bad. I'm still waiting for it to pull up.
Okay.
I'll write it down though, so you can move on if you need to.
I'm only seeing 19 and there's 26 of y'all here. Okay, I'm gonna minimize this, but you can still log in. The attendance code is at the bottom right-hand side. So we're just gonna do one question right now, and then we'll do our second question later. So the question is, will the methylene hydrogens be shifted upfield or downfield? Okay, about 10 more seconds to submit your answer. Okay, so we have one vote for no shift, 7 votes for they'll be shifted upfield, and 15 for downfield. The 15 of you are correct. So the methylene hydrogens being closer to the fluorine will be shifted downfield further away from 0. Great. So we're gonna end this, we'll come back to it. I'm gonna push new share and go back to our PowerPoint before I start asking you guys questions about it again. Okay. So the next bit of information that we can get from a proton NMR is from the intensity of the signal. So the area under an NMR signal, the integral, is proportional to the number of protons absorbing energy at that position. So an NMR spectrometer can integrate the area under the peaks and print out a stepped curve on the spectrum. The height of each step is proportional to the area under the peak, which in turn is proportional to the number of absorbing protons. Modern NMR spectrometers calculate and plot the value of each integral in arbitrary units. And the ratio of integrals to one another gives the ratio of absorbing protons in a spectrum. I want to reiterate again that this is giving a ratio and not the absolute number of absorbing protons. So we're going to look at an example in a second because it'll make more sense, I believe. So a little history on the integral of an NMR spectrum. So first of all, older NMRs did not actually print out any sort of number indicating the value of the integral. So here the NMR was giving 1 and 1.5. So this is a ratio. You can't have 1.5 protons. So when you see values of 1 and 1.5, you have to start multiplying by 2 to get to a whole number. So, or whatever you need to multiply by to get to a whole number. If it said 1.33, you'd have to multiply times 3. So if you multiply both of these numbers by 2, you would get a ratio of 2 to 3. So 1 to 1.5 is the same as a ratio of 2 to 3, which is the same as a ratio of 4 to 6, which is the same as 8 to 12, and so forth. You could keep going, right? What this means is that the NMR could be representing compounds with any of these numbers of hydrogens. You have to use the molecular weight, or maybe if you have the formula, or maybe you did an experiment to synthesize a compound, so you have a good idea of the number of carbons present. You have to figure out which one of these ratios is actually being represented by the spectrum. Now, the fun part is that in the olden days of NMR spectroscopy, which is really not that long ago, the machine didn't put out numbers at all. It just put out a curve. And so they would use rulers and actually measure it out and then say, okay, well, this one is about 6 centimeters. This one's about 9 centimeters. And then they would have to do the ratio from there. And that was how I learned how to do NMR, even though I did my learning in the age of modern NMRs, where they did put out numbers. I guess my professor just wanted us to whip out rulers and measure integrals. But anyway, so you guys are actually given numbers, which is great. And you can, excuse me, you can go from there to determine how many protons it's actually representing. So this peak here is representing 6 hydrogens. And we're going to analyze this structure a little further real fast. So ignoring the integrals right now, we have 2 unique signals. We have one at about 2.25, and then we have one at almost exactly 7. What else can we say about these signals?
They're single peaks.
They are, right. They are what's called a singlet because they are just one single peak. If something is a singlet, remembering that we get our splitting pattern from the N+1 formula, where N is the number of neighboring hydrogens, how many neighbors must each of these hydrogens have? If it's only split into one peak?
0.
0, right. So if we look at the structure that they actually gave us, we'll see that this is correct. These hydrogens on this carbon, their neighboring carbon is this one. Are there any hydrogens on that carbon?
No.
No, it's double bonded.
Right. So there are no hydrogens on this carbon, which is why this signal is not split at all. The other set of hydrogens are these. Now, they do have each other as neighbors, but something we didn't really talk about is that you cannot split yourself. So this hydrogen is equivalent to this one. They are not going to split each other's signal. They're going to share a signal. You can only be split by a proton that is different. So even though they have neighbors, the neighboring carbon that is not identical has 0 hydrogens on it. So that's why this peak is not split either. Now, the other bit of information that we can get from this is based on their chemical shift. So this 2.25 is quite a bit high for a methyl group, but it's not high for a methyl group coming off of an aromatic ring. That would be about right. And then these are representing the hydrogen that are directly attached to the aromatic ring, and 7 is pretty typical for something directly attached to an aromatic ring. So if you know your chemical shifts, this structure would actually be really easy to solve without this information on here at all. You could come up with this pretty quickly if you practice. Okay, are there any questions about the integrals before we move to the top hat question?
One question real quick. So
Mhm.
how do you know the 4H and the 6H?
So it was you were given 1 and 1.5. And so from there, you know that your ratio is either 2 to 3, 4 to 6. I guess 6 to 9 would also be a valid one that I didn't write, 8 to 12, and so forth. From there, you'd have to use other information. So if you were given the mass spec, you would have the molecular weight. So then you would know it can't be 2 to 3 because that wouldn't be a heavy enough compound, and it can't be 8 to 12 because that would be too big. So a lot of this information you have to use combined, essentially. Also, this hydrogen being pretty obviously an aromatic hydrogen, and I say obvious not because I would think you guys should find that obvious, but because I've been doing NMR like, during grad school. I did it every single freaking day of these just giant compounds. My spectra were these just giant disasters that I had to analyze. So I'm pretty good at NMR. So when I look at this, I say that is aromatic, and I'm pointing and you guys can't see that. I say that is aromatic and that is a methyl group on an aromatic ring. So the more you practice, the more that becomes kind of built in. And I do want you guys to practice. I do want this to become kind of built in. I know that a lot of you are not ever going to do chemical research and have to do NMR. But NMR is tested on the ACS exam. It is a topic that you guys are expected to know leaving OCHEM 1 and especially after leaving OCHEM 2. So it is
Okay.
one of the goals in OCHEM.
Okay, thank you.
Mm-hmm. Okay, let's go back to Top Hat. I'm going to share the Top Hat screen this time. Okay. What will the ratio of signal intensity be for the protons of the following compound? Okay, another 10 seconds to finish up your answer. Okay, one person still has to answer. You have about 3 very long seconds. Okie dokie. Okay, let's see what we got here. Okay, so these are all really different answers, but there is something here that I actually really appreciate. So it looks like a lot of you were recognizing that these 3 methyl groups would be identical to each other. So these 9 hydrogens are identical. And then you have this OCH3 group. These 3 hydrogens would be different from these other ones. So you have a ratio of 9 to 3, which simplifies to 3 to 1. So the people who put in 3 to 1 are correct. But I feel like a lot of these were kind of seeing the right idea. So that makes me really happy. Okay, let's go to our PowerPoint. So I want to share with you guys a little information about NMR also. I don't know why this isn't in my slideshow because I always talk about it. So NMR, this has a very specific chemical application, obviously, but NMR has been in development for such a long time. The Nobel Prize in Physics was awarded in 1943 to Otto Stern, a scientist from the United States, for his contribution to the development of molecular ray method and his discovery of the magnetic moment of the proton. That was followed by a Nobel Prize in Physics in 1944 for Isidore Rabi, also from the USA, for his resonance method for recording the magnetic properties of atomic nuclei. Now, this keeps going. I'm not going to read all of the Nobel Prizes related to NMR, but what's really interesting about this is that NMR also has some really significant medical implications. If anybody's ever gotten an MRI where you're put into essentially a giant magnet, you're injected with a dye typically for an MRI, which is going to have some sort of predictable magnetic response. MRI is just an NMR for a human body. So it's the exact same science, the exact same technique. And it was developed for chemistry first, and then it was realized that this could have some interesting health applications. The Nobel Prize for that, the Nobel Prize in Physiology or Medicine in 2003 was given to Paul Lauterbur from the United States and Peter Mansfield from the UK. And that was for their discoveries concerning magnetic resonance imaging, which is the MRI. And that was only in 2003. But anyway, so the Nobel Prize for NMR has been happening for a long time, since the 40s. And then in the 90s, I believe it was 91, was the Nobel Prize that was awarded for what we now use as NMR, as chemists, high-res NMR, essentially. So much, much better NMR. So another type of splitting is the spin-spin splitting. So spin-spin splitting occurs between non-equivalent protons on the same carbon or adjacent carbons that are more than 3 bonds apart. So a doublet occurs because you're being split by 1 hydrogen on an adjacent carbon. A triplet would occur because you're being split by 2 hydrogens on an adjacent carbon. So in this compound here, we have 2 types of hydrogens. We have a single hydrogen, which is called a methine hydrogen, but it's spelled METHINE, not YNE, because it's not referencing a triple bond. It's referencing being a CH. So this methine proton has 2 neighbors. So it is being split into a triplet. The methylene protons, which again is the term for CH2 protons, have a single neighbor that is different. And so they're being split into a doublet. So there are a couple rules for splitting. First of all, equivalent protons do not split each other's signals. They will share the same signal and they will not be split. There's the N+1 rule, which we went over. Splitting is observed for non-equivalent protons on the same carbon or adjacent carbons. So if you have two protons that are on the same carbon that are not identical, they will split each other's signals. So think of that cyclopropane, chlorocyclopropane that we looked at previously. We had the two CH2 carbons that each had two different types of hydrogens on them. Those two different types of hydrogens would split the signal. If you had an alkene that was asymmetric, so say, there's two different things happening over there, proton A and B would be different and those signals would split each other. When HA and HB are on adjacent carbons, Dad, I'm teaching right now, stop calling me. When HA and HB are on adjacent carbons, if they are not identical, they're going to split each other. So the most common splitting that you'll see is this neighboring carbon scenario, but occasionally we'll look at some trickier examples with protons on the same carbon. Do we have any questions? I think it's been a while since I've asked for questions. Okay. So there are some splitting patterns that you can hopefully kind of start to recognize. So when you have two tertiary carbons next to each other and you have two unique methine protons next to each other, they each only have one neighbor, so they will each show as a doublet. If you have a CH2 group next to a CH, a methine, the CH2 will appear as a doublet because they have one neighbor. The methine will appear as a triplet. Right, I'm not gonna keep walking through this, but there are some that you just see all the time. So an ethyl group is a really, really common substituent. And so anytime you see a triplet and a quartet very near each other, it's probably an ethyl group. That's a really, really common motif. Okay, I believe this is just a very repetitive slide, but I want to go through the structure of propane with you guys. So propane does have a mirror plane running through it this way. All right, so we have a unique carbon with a set of unique protons, and then these two carbons are identical, which means all 6 of these hydrogens are identical. So what we ultimately have is 6 HBs and 2 HAs. What is our ratio of our, I'm gonna cross it out so you can't see the answer if you haven't read it already. What is the ratio of the integral?
Uh, 3, 4, 3.
No, because we have 6 HBs and 2 HAs, so it should be simpler than that.
3 to 1.
Right. It'll be a 3-to-1 ratio. And that's just because we have 6 of the HBs and 2 HAs. So if you write that as a ratio, it's 6 to 2, and you can simplify that to 3 to 1. The methyl protons are going to resonate at a lower chemical shift because they are methyl. And then the methylene protons will have a slightly higher chemical shift just because it is a secondary carbon. I also want to look at the splitting here before we move on. I know that they already drew out and labeled all the peaks and such, but I want to look at the structure. You can actually predict from a structure, what you should be seeing. So how many neighbors do the HA atoms have? How many neighboring hydrogens?
6.
6. So HA should be split into 7 peaks, which is what we see. How many neighbors does each HB hydrogen have?
2.
2, right? The neighboring carbon has 2 hydrogens. So that makes it split into a triplet. I really like this slide. I took this from Top Hat. If you need a good summary later of how to read NMR, like you need a slide to kind of like jolt you back into it when you go to do practice problems, this is a really good one. It explains in detail what you're looking at when you look at an NMR. So it talks about what you should expect for the integral. It talks about why the splitting patterns are the way they are, and it points out the chemical shifts. So this is a good place to start back over again later if you need to. Okay, this is the same molecule that we looked at way in the beginning, CH3CH2Br, bromoethane. I don't think we need to go back over this again because we kind of hit on it earlier, but it's revisiting the splitting patterns. This would be another good example to go back over later. Okay, our last topic is spin-spin splitting, which is when you have different neighbors. So when you have 2 sets of adjacent protons that are different from each other, and you have so N protons on one adjacent carbon and M protons on the other, the number of peaks in an NMR signal will be N plus 1 times M plus 1. So what that means is this poor CH2 set right here is going to have some very confusing splitting. So HA is going to be relatively straightforward. It has 2 neighbors. HA would be a triplet. So this one should show up like this. HC also has 2 neighbors, so it would show up as a triplet. That would be really, really straightforward. But HB has a much more complex situation. So it has 2 neighbors on the right and 3 neighbors on the left. Those neighbors are not equivalent to each other, and so their effect on HB and its splitting pattern is going to be different. So the way that you can look at it is HA is going to split HB into a quartet, but HC would split HB into a triplet. So what you end up with is a quartet of triplets. If that makes sense. Are there questions about this? This is kind of weird. We don't, I don't make you guys analyze this too much, but this is something that you see a lot of.
So what decides what would be the, I guess in this instance, the broader quartet and what would be the localized triplets?
So that's going to be based on the coupling constant, which is a value that can be determined experimentally through NMR. And it can also be a value that you could look up. If the coupling constant between JAB is greater than the coupling constant of JBC, then the JA splitting will be prevalent and will happen first. So that's what the situation is here. If JBC were the greater coupling constant, we would have a triplet of quartets. But I don't give you guys coupling constants and then ask you to determine what the splitting pattern is going to be. I think that's quite a bit beyond OChem 1. If you end up taking advanced OChem, or if any of you go to grad school for chemistry and you take a spectroscopy course, that's when they'll make you suffer and go through that. It can be very, very useful information, but in my experience with NMR, unless you have a very, very high-powered instrument, you're never synthesizing anything so small and so clean that it would be that useful. For some of my compounds, my boss made me calculate the coupling constants for publication and stuff, but it's not, I'm not gonna make you guys worry about that in OChem 1. Mostly, I want you to be able to understand when you see something like this, why in the world that would happen. I also want you to know that it's 12 peaks, because whether it's a quartet of triplets or a triplet of quartets, it's still 12 peaks, and that's calculated in this way. So this is calculated as, so remember, we're talking about HB here. 3 plus 1 from this guy times 2 plus 1 from this guy. So that comes out to 4 times 3, which is how we get to 12 peaks. But whether it's a quartet of triplets or a triplet of quartets, I don't care if you guys can predict that. I just want you to know there should be 12 peaks. Does that simplify it enough for? Okay. And then there's this last sentence here, which is kind of an unfortunate thing that happens a lot. When JAB and JBC are similar in magnitude, the peaks will overlap and you'll see fewer lines. So you can expect to see 12 peaks, but you may not. And that will come down to integration typically. So using the integral to determine how many peaks or how many protons are actually there. Okay, let's go to top hat again. Yeah, so just keeping in mind that this is OChem 1, you're gonna get largely fairly simple NMRs from me. So match the following areas with the appropriate proton splitting pattern. Oops. Is it open?
Yeah.
Okay, yeah, there you go. Okay. Okay, about 10 more seconds to finish answering. Okay, let's see what we said here. Okay, so we have 12 people in agreement roughly, or maybe 12 people said A is triplet and so forth. Let's go through this real fast. So A has how many neighboring protons?
2.
2. And 2 plus 1 is 3, so that should give us a triplet. B has how many neighboring protons?
3.
3. So that would give us 3 plus 1, which is 4. So that would give us what?
A quartet.
A quartet.
Quartet.
Yeah, so we should have triplet, quartet. And then C has how many neighbors?
None.
Right, it has 0 neighbors. So that would be 0 plus 1, which gives us a singlet. So for the most part, we did okay. Not too bad. Are there any questions about this? Looks like about a quarter of you got all 3 correct, which is great. Okay, let's go back to PowerPoint. Oh, this reminds me. Sorry, before we move on with the class, but with the lecture, I'm going to stop sharing for just a second. In my email to you guys, I wrote that there were a couple potential changes that I thought we should make. So the first one is we're supposed to have our exam this Friday, but I think the better choice would be to go ahead and try to get finished with all the material and then take the exam on next Tuesday or Wednesday. That does a couple of things for us. It lets us finish the material so that we're not just like stopping and then starting back up again. And it gives you the weekend to study and do practice problems, which I think is really, really valuable. The other thing is that then we would have to put the quiz this Friday, which I don't think anybody would be really opposed to having a quiz instead of an exam. So we'd just be flip-flopping them on the schedule. So that's motion 1. Does anybody like have any potential issues with that? I might actually go ahead and put the effort forth to create a survey real fast. Okay, and then the second proposal is adjusting the scale of some of the grades. I think it was to change participation from 20% to 15%. And change homework from 10 to 15%. So the reason that I'm suggesting that is that a lot of you have really high homework grades, and then participation is a little bit of a struggle. So I do want to keep participation at 15% because it's you guys' attendance, which isn't put in yet. And it's also your answering questions during class, which is really important when you're trying to keep everybody on board during an online class. So I'm going to send out a poll so that you can answer me privately. So just go ahead and answer yes or no to both things. So then if anybody has an issue, that can be private. And if the majority of students agree, then that's what we'll go with. I see a question. The final exam will not be the ACS exam. It's a controlled exam. We can't do it online. That's a violation of the exam procedures.
Are you meaning like Tuesday of like this week, like this coming up week, like tomorrow?
No, it would be Tuesday, August, whatever. August 4th. And then that would give us the 5th to do a review day, and then your final exam would be the 6th. Because I do think we're going to finish the material in time to have a review day. I'd be surprised if we had material left this week. If we finish all the material this week, we can do a review day on Monday, and then we could take Wednesday off if we wanted, or we could have an optional class on Wednesday. We'll see. Okay, one person left to vote. Go ahead and get your vote in. So far, the motion on the exam is 100%, and it looks like there are a couple people disagreeing with the split up. We have a 92% agreement on the changing the participation in homework. So we'll hold on that one. If you disagree with that one, send me an email and kind of give me an understanding of why, and then we can try to talk about this again tomorrow. That doesn't have to be an immediate change.
For the homework due on Friday, would that be extended to
I would
the
do
10th?
that. Yes. Yeah. Okay, so I'm gonna go ahead and end the polling. So the motion basically broke down like this, so you can see the results there. So yeah, we will move the exam to next week. I think that's best for everybody. And then we'll revisit the percentages. Okay, cool. Thank you guys for letting us take a moment to do that. Okay. I feel better about asking privately because then if anybody has issues, they can actually disagree. It's hard to disagree with your classmates. I see chat. Okay, it's just everybody telling me how great I am. That's the best type of chat. Thank you.
So the test is going to be on Tuesday?
Yeah, the exam will be Tuesday. I'll send out an email after class to summarize the changes to the schedule. And then I'll change our homepage to represent that as well. Okay, so the next topic is the protons on non-carbon atoms. So these are going to be OH and NH protons largely. Now the issue with these is that they are susceptible to hydrogen bonding with each other. So if you have a solution of ethanol, there's probably going to be hydrogen bonding between ethanol molecules. If you have any water in your sample, you're going to have some confusing hydrogen bonding between ethanol and water. And that will have an effect on the signal that you see from the hydrogen. So first of all, I want to point out that the hydrogen on the oxygen atom is not split. Even though the carbon next door has 2 hydrogens on it, there is no splitting seen by that hydrogen. So that's one sign that you have an OH proton. The shift is also a little further down. Notice also that the CH2 group is a little more downfield than normally would be, and that's because the carbon is directly attached to the oxygen. Excuse me. Under usual conditions, an OH or NH proton is not split. Its NMR signal is not split by adjacent protons. Adding a small amount of D2O, so deuterium oxide. Deuterium is H2, so it's a heavy form of hydrogen. It has an extra excuse me, neutron to the NMR sample will cause the OH or NH absorption to disappear entirely due to what? Oh, sorry, I thought I heard a question. So what happens essentially is since the hydrogen on the ethanol is covalently bonded, yes, but it can also exchange pretty easily if you have an excess of D2O. You're going to have some acid-base chemistry that could cause exchange to the point where you now have an ethanol where instead of the proton, you have deuterium. And so that's going to cause the absorption to disappear. Okay, this one I think is probably some of the more confusing material. I'm gonna go ahead and tell you now, we don't do a lot of cyclohexane NMR. I am going to show you some of the complications that can arise from cyclohexane conformers, but most of the NMR spectra that you'll see from me will be either straight chain, so linear alkanes with functional groups, or aromatic. You're not gonna see cyclohexane from me usually. So the first thing to note is that axial and equatorial hydrogens rapidly interconvert through chair flips. So as long as there is a reasonable equilibrium between those two protons, the NMR is going to show an average environment and you're only going to see one signal. So even though HA and HB are unique protons, especially if there are substitutions on the ring, typically you see an average of those two signals. Now, if there is something on the ring that is forcing only one chair conformer to exist, so you may remember when we did the example of methyl chloride and neomethyl chloride, that I believe it was the methyl chloride, really only had one valid conformer. In one conformer, all three substituents on the cyclohexane ring were equatorial, and then the other one, all three were axial. And we said the version where all three are axial is virtually never going to exist. So if you only have one conformer existing, you're going to see a very specific NMR. But if it's rapidly converting, you're going to see an average of that signal. So at room temperature, ring flips are very rapid. The NMR is going to record an average. If you want to see specific peaks, you can actually cool the sample down. And that can help you see both peaks for one signal. Mostly when the samples that we look at, we'll be seeing an average. And again, we don't do a lot of cyclohexane NMR anyway. I mostly show it to you because there's probably at least one homework problem with it in there. So benzene rings, you're going to see a lot of them. Most of my problems that I give tend to be substituted benzenes. So benzene has 6 equivalent D-shielded protons and exhibits a single peak in its NMR spectrum at 7.27 ppm. So remember, benzene is just C6H6. And so all 6 of those hydrogens are equivalent, and that also means that they can't split each other. So you just have a single singlet at 7.27. When you have a mono-substituted benzene, meaning there's one substitution on the benzene ring, you're going to have 5 D-shielded protons along the benzene ring, and they're D-shielded because they're on benzene. They are no longer equivalent because you've now created something that brings in a little less symmetry. So benzene is symmetrical in so many ways. You can draw a mirror plane across carbons, across bonds. There are so many planes of symmetry in benzene. When you introduce one substituent, you now only have one mirror plane. So we have 3 unique protons. We have our HAs. These are one set. We have HBs and HC. So 3 sets of protons. Now, how these signals actually appear is going to highly depend on the identity of Z. If Z is very electron withdrawing, that's going to have a much larger effect than if it was more electron donating or more neutral. Also, you're going to see some differences in the integration. Each of these would be represented by a peak of 2 to 1. So you should see a ratio of 2 to 2 to 1 if they are separated out. A lot of times aromatic protons just end up kind of in one big cluster. So for example, you can tell I remembered that this slide was animated that way. If we have ethyl benzene, we kind of end up with a cluster of benzene peaks. That would be very, very fun, I'm sure, to try and identify. Benzaldehyde has something really interesting going on here. So these protons, you have sets like this and then one individual one. These 3 protons are probably represented here, while these 2 are represented here. And now if you have a methoxy group, you actually see even more separation across the signals. But again, notice these are kind of a disaster. So monosubstituted benzene ring NMRs are often really messy, very difficult to interpret. But when you introduce di-substituted structures or even tri-substituted, if there's symmetry, you can actually get really, really simplified NMRs. So for example, this one has a mirror plane, right through the middle. That was a horrible line that I drew. You have HA and HB. HB has one neighbor, HA has one neighbor. So they are each represented by doublets, and they are separated by almost 1 whole ppm, probably about 0.8. HA, being closer to the bromine, is further downfield. HB is closer to the ethyl group, so it's a little more upfield. So basically HB has not really changed at all from what the NMR shift for benzene would be. And then the other interesting thing about this spectrum is that you see the traditional ethyl group here. So you have your CH2, which has 3 neighbors. So it's going to be a quartet. And then you have CH3, which has 2 neighbors. So it's a triplet. This is the type of structure that I like to give on a quiz or an exam. Something that can be very easily turned into a structure. So you could be given like this NMR and an IR, some mass spec information, and you could come up with the structure. We're not going to get quite to there today because it's 11:28, but we're going to do some practice problems tomorrow. Okay, so let's look at, whoops, I didn't mean to shut that down, but I did. We're going to go to Top Hat and do one more question. Okay, so this one is a little more complex, but I think with a little bit of effort, we can do this. So which structure do the following spectra most likely correspond to? So you're given an IR and you're given an NMR. And then you're given 3 structures below. I'm going to give you about 4 minutes to make your decision, and then we'll go through how to determine between the 3 of them. And that'll probably finish us up for today. Still about a minute and a half to submit. Okay, about 30 seconds to finish up. Okay. Okay, so let's go through this before we put our answers up here. So there are two ways that you could do this. First of all, hopefully you notice like the IR, it tells you there's a carbonyl, right? That's what that peak there in the middle says. It says there's no OH group, so there's no carboxylic acid, no alcohol. But if you notice in here, you have one ester, a ketone with kind of a broken up attempt at an ester, and another ketone. So if you were really, really good at IR and you can see the CO bond in there, that could be useful. But the NMR can also help you solve this. Woo. Go back, go back. Oh, no, I see what happened. Oops, sorry. I just shrunk the image, that's all. It's really the NMR that can help you get the answer pretty quickly. So what I would do if I were you is I would backtrack. I would start with the structures and see what the NMR should look like if I had this structure. So if we had, let's start with this one, the one on the right. This one's actually the easiest one, I think. What would these hydrogens show up as? What would their signal be? Would it be a singlet, a doublet, a triplet, a quartet? Does it have any neighbors?
No,
No. So how would it show up?
it'd be a singlet.
Yeah, that would be a singlet. Do we have any singlets in our NMR spectrum?
No.
No.
No. Both of these are CH2 groups. They both have two neighbors. So that would be two triplets, right? Which we do have. But notice we have a triplet worth 2, and our other triplet is worth 3. So this actually tells us that if there's an integral of 3 for this triplet, that this is a CH3 group next door to 2 hydrogens. This group here is a CH2 group that only has 2 neighbors. So that tells me that we have a CH2 group with something else over here that we don't know, something else over here that we don't know. So that definitely discredits this structure. This one over here has another very similar issue. This carbon, or these hydrogens, don't have any neighboring hydrogens. We would have to have a singlet in our NMR spectrum in order for this to be the case. And also we would see the traditional ethyl pattern. We would see a quartet and a triplet, which is not something that I see in this structure, right? Now, the difficult thing is that it's really hard to tell how many peaks are in here. I tried counting a couple times. I think I only see 6. But who knows? So, and this doesn't tell you anything. It just tells you it's a singly substituted benzene, which we already know. So then I would look at this structure and see if this matches more closely. So this methyl group, how many peaks would it be split into, its signal? How would it appear on the NMR? As a singlet, a doublet, a triplet, a quartet?
The one on the very right?
Yeah, so this methyl group, how many neighbors do these hydrogens have?
2.
2.
Yeah.
So it would appear as what?
Triplet?
A triplet. And would it be more upfield or downfield?
More downfield? Or sorry.
Right, it'd be more upfield, right? So it's pretty reasonable to think that, sorry, I'm gonna erase all this stuff here. It's pretty reasonable to suggest that this could represent this one down here. So we'll call this A, B, C. This could definitely be the signal for the A protons. Now, our B protons have 2 neighbors and 3 neighbors, right? So that would be 2 plus 1, which is 3, times 3 plus 1, which is 4, which gives us 12 peaks. That's not what I see here. But again, it could also be that their coupling constants are really close together, and so we're not seeing 12 peaks. So I'm going to skip over that for now. These 2 hydrogens are being split into a triplet. So that must mean that these 2 hydrogens have 2 neighbors. So that's what makes me pick structure A, is that for the most part, the splitting pattern actually matches up here. Also, the pieces that we were drawing out earlier can be seen in this structure. You can actually string these together. This CH2 and this CH2 are the same. So that gives us CH2, CH2, CH3 as a potential string within the molecule. This is the only example there. So that's what would make me pick A.
So, real quick question. You said that it would be 12, but why wouldn't it be like 2 plus 3 plus 1, so 6? You know what I mean?
So the formula for this is M plus 1 times N plus 1. So that would give us 2 plus 1 times 3 plus 1.
Okay, that makes sense. Thank you.
Because these hydrogens are different from each other. Okay, I need to close down the annotation so I can move forward. And it looks like most of us voted for B, but 8 people voted for A, which is great. Are there any questions about this? Did the process that we just went through make sense?
Yeah, it did. Thank you.
Okay.
Yeah, I think I had the start of the right idea anyway.
Okay. Cool. So, okay. I know class is over, but I want to show you what we're doing next in class. So, the next thing we're going to go over is carbon NMR. We're not going to spend too much time on it. It's pretty easy to look at. And then we're going to go through these spectra where we have an IR, a mass spec, a UV vis, and carbon and proton NMRs for compounds. And then we're going to identify from 4 compounds which one it is. And I have 3 examples of this. I would really, really like for each of you to work on these on your own before we get to class. It'll make it go much faster, and also me explaining to you why the correct answer is correct is much more effective if you spent time struggling over it yourself. So if you didn't look at this at all on your own and then I give you the answer, you literally get nothing from it. But if you work on this on your own and you come up with your own ideas and you come up with your own questions, and then we work through it together, you can see why your correct idea was correct or why your incorrect idea was incorrect. It'll be so much more helpful for you if you maybe spend 10 minutes on each one. And if you get it within 10 minutes, great, move on. If you after 10 minutes you still have no clue what the correct answer is, that's fine. But, you know, cover these in your notes, you know, figure out like, oh, I know what this peak on the IR means. I'm going to look at this NMR. Okay, I get some of this, maybe I have some ideas. Just try and struggle with the material a little bit on your own before you get to class tomorrow. But that's it for my request. Make sure you're working on your homework. There's a lot of it. I know that the homework assignments are really long. I deleted some questions, but I left them long because practice is ultimately the best thing you can do in this class. So I'm going to kind of force you to practice. But yeah, I will see you guys tomorrow.
Thank you.
There's